my favorite parts in transport phenomena are fluid mechanics, this perturbation analysis, and whatever we will be covering in context of transport in electrolytes. We do a little bit of diffusion, and the diffusion is always something we end up seeing in context of how polymers move, particles move. I hardly do any heat transfer, so I enjoy teaching it, but not as much as I enjoy teaching this bit. So I'm looking forward to these topics. So one of the important things we want to remember is the regular perturbation analysis. When we'll see these steps implemented today, but it's a way of solving a problem which involves sometimes simplifying a nonlinear problem by using a small parameter, and with the help of small parameter we get like the first order correction to a simple solution which we would have if those say in this case temperature dependence were not involved. So the problem that we are looking at is electrically heated wire, and electrically heated wire problem is sort of the first problem we discuss in this course. It's also, if you go through Bird, Stewart, Lightfoot, it's the first problem that they discuss for undergraduate heat transfer. And the idea is that in a general sense, there's always going to be a conversion of electric current to thermal energy, and when that conversion takes place, if you're looking along a wire, that conversion is taking place at every step along the way, and that causes heat transfer outwards. And when there is heat transfer outwards, you can have some boundary condition at the interface between the solid electric wire and the surrounding fluid. The surrounding fluid would be air in many cases. When I was in undergrad in IIT Delhi, and we sometimes ran out of hot water, we used to use these electrical wires in buckets, and that's very risky, but yes, that's what. So there it used to be a fluid which was water in that case, right? So, and then when you start out, the water is not moving, so then the boundary conditions are easy, but if water starts moving, then you know you need the heat transfer coefficient. The thing that we don't really get to do in this course, but I think for completeness I should say is, so the heat transfer coefficient and mass transfer coefficient are important ways in which chemical engineers solve really complex problems, and those the values, absolute values of heat transfer coefficient or mass transfer coefficient depend not only on material properties, but they also depend on geometry, and they depend on flow characteristics. So the best way to figure out what your heat transfer coefficient is going to be, or mass transfer coefficient is going to be, is to just pick say BSL and go to your geometry. If it's flow around a cylinder, there are specific correlations. You look at those correlations, you just calculate the number and use it in an equation. We can derive some of those correlations, but more often than not, those are engineering correlations that people have determined either from lots of experiments or compilation of lots of data. And so when you look at those correlations, usually below the formula they'll say it's valid for this range of velocities or this range of dimensionless numbers. So that's something we say for completeness. If you do, so when I have to teach that at an undergraduate level, we spend maybe a few weeks discussing those, because in industry you use many of those correlations and you just need to know how to plug in numbers, right? All right, so that's one set of things to remember. Now in this context, the first thing we identify or realize yesterday is that in real life, both the conductivity or thermal conductivity and this heat source term can be temperature dependent. And if they are temperature dependent, then it makes this equation into a nonlinear equation, because this depends on temperature, temperature depends on R. So if I have to take the derivative, for example, now I cannot really pull K out. Right? So I cannot pull K out because if you take the derivative, you'll need to do differential by parts and you'll get 3 terms. And then it just begins to unravel into a very complicated problem from there on. Now, every time I have a temperature dependence or a concentration dependence, you have to figure out what that concentration dependence is and what the temperature dependence is. What you'll find is this linearization is always a good first estimate. So when you do your research, you'll find dependencies that go any which way, right? So it could go this way, that way, all these are curved. But if I select a very short range of data, then it looks linear, right? So that's the joy when you're doing a theory and you can apply the perturbation analysis, because you can always say, okay, I'm just looking at a small region. That is the risk when you're doing experiments, because if all your data points are here, 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 then you do one experiment and you say, oh, this is not matching my data, but sometimes you have to investigate more because there might be something else that's causing this curvature to appear there. So as a simple first approximation, we say this dependence is linear, and we make the same kind of assumption for both conduction and for the source term. And then yesterday we gave the physical argument that if it's a metal wire, then this value of A is going to be the same. So once we accept those assumptions, now all of them are assumptions that can be easily criticized, easily violated. If your T minus T naught is slightly large, maybe this is not going to be enough. You need another term or more terms, and the linearity might not hold. But assuming everything holds, all the assumptions are correct, then we saw yesterday that if we use this equation, then from this equation we can estimate what our temperature scale is going to be. So that temperature scale turned out to be this quantity divided by this quantity, and then you have to take care of all the length scale, so it's becomes temperature. And you can look at this here itself. So this is R and R cancels out in your order of magnitude analysis. So this should be T over R squared into K, and that should be the same order HV, and that immediately gives rise to this. Right? So you can go back and forth and check everything. Other way to do it is know that this is heating rate, so it is heat per unit time, and then know the units of this, know the units of this, and check that it's dimensionless. Now I'm emphasizing that because in exams especially, we make errors where you can fix those if you just keep an eye out for the right dimensions. And here I can see this into this is dimensionless, so I have to multiply A with my scale of temperature. So once I have done that, I will call it a small parameter as long as this A compared to my temperature scale, or if I wanted to write it as a ratio, I am going to write it as, because this is inverse temperature, so this is being compared to your reference temperature, and that ratio, as long as that ratio is much less than 1, we can use the series that's going to be the step 1. But before we get to writing down the series, let's write down the differential equation. So now a differential equation has to be written in terms of these dimensionless groups, and also we are going to use the expansion. So 1 over eta, d over d eta, so that's r is being converted to eta. Then you have again r there, and it's multiplied with 1 plus sin theta d theta over d eta, because I have now taken the expansion. And so when you do this, when you repeat this yourself, what you need to learn how to do is, I can write, there are 2 ways in which you can do this. So for example, if I had to write this term, right? So if I I were to write this term in terms of those variables, some people like to do it this way. So then you're just using the equality, and then I can go write d r eta, and then inside I write r will be capital R eta, and then k will be k, and then dt you again are going to write as d multiplied with h infinity r squared over k multiplied with d minus, so get theta here, so that is, and the theta here, and okay, so that's d over, so I have all the terms, right? And then I have downstairs. So of course, when you write it like this, then you know everything you're scaling with, like this r and this r and this r, they are constant, so you can pull them out. And whatever is not a constant, you have to watch it when you're taking the derivatives. So I would want you to do those kind of steps for practice, because you can write these things down in detail in class, but it's in one sense it's algebra, but in another sense it makes us go slower, and we don't really get to the physical insights that are more critical, right? So that's the equation, and then we have the boundary conditions. The boundary conditions become d theta over d eta at 0 is 0, and then theta at 1 is 0. So again, emphasis is this is a nonlinear equation, and it's a nonlinear equation because the coefficient of d theta over d eta depends on theta. And for that reason, this kind of problem is going to be tricky to solve if I did not place a restriction on the values of epsilon. So when I place a restriction and I say epsilon is really small, I can solve it. If I don't make that restriction, then it's trickier. You can always go and use numerical methods. But in numerical methods too, what you learn over time is it's very easy to program something and then have sort of a numerical errors that will blow up, and if you don't know your analytical methods well, it's very hard for you to check them. Experimental checks you can have often, but then experimental checks will also tell you maybe your numerical solution is correct only under some assumptions, and you can't really check whether the math is right or not unless you have some other way of decoding. Okay, so for epsilon much less than 1, solve using regular perturbation analysis. And let's do the step 1. So the step 1 is we are going to state power series involving epsilon. So epsilon here is in some sense a ratio of a constant. If I fix the temperature, if I fix the material, then this is a material dependent property. Of course, it depends on the choice of material, but once I pick the material, then this is a constant. And then this whole scale, because I'm evaluating K and H at the ambient temperature, which is T infinity, so all those things are also constant, and my wire size is a constant. So even though this is a constant, the first step involves writing a power series where we are going to treat epsilon as a variable. So, and then we treat epsilon as a variable, and then we try to find solutions first for the case when this epsilon is 0. So when the case of epsilon is 0 is equivalent to A being equal to 0. So if I look at the problem statement again, if my A was equal to 0, then these things are not temperature dependent. If these things are not temperature dependent, then I go back to the solution we unraveled or uncovered last week. So epsilon equals to 0, we know the solution, and that's a simpler solution. But now if epsilon being a variable somehow starts to be greater than 0, then we need to figure out what that solution is, as long as it's much less than 1. The other thing that is mathematically robust and is easy to appreciate is, so let's say epsilon is 0.1. So if epsilon is 0.1, epsilon square is going to be 0.01. Epsilon cubed will be 0.001. So when it's 0.001 multiplying whatever, if that thing is of the order 1, then 0.001 is negligible compared to 0.1. So when we have a power series with epsilon square, epsilon cube, epsilon 4, epsilon raised to power 5 terms in front of it, as you go to higher and higher order terms, they automatically become negligible. And so if everything we are doing is done consistently, then all we need to know is maybe we need epsilon raised to power 1 term. In some cases, we'll go up to epsilon raised to power 2 term, and we'll probably usually stop there, because you can do the extra algebra, but it's not going to improve your solution by too much. So that being said, now let's actually go through the process of solving this. So we start by using this expansion, where we need to write it as a series. So we use Taylor series, and when we write Taylor series, we write this Taylor series about epsilon equals to 0. So we end up with coefficients that depend on eta, whereas this epsilon has powers of n. So the temperature, dimensionless temperature, depends on the radial variable. Epsilon itself does not depend on the radial variable, so all the radial variation is captured by coefficients. Because it's Taylor series, it has infinite terms, but as I'm going to have epsilon to be a very small number, it will be turn out to be something where we need only a certain number of coefficients, and we get to decide how many we want. And we need to remember that this is Taylor expansion about epsilon equals to 0. So the other thing, okay, I can just write it down, that theta n, the coefficients theta n capture the radial variation, and they are independent of epsilon. Okay, so step 1, state power series, done. Now let's go to the next one. You have to expand governing equations. So governing equations are this equation and the boundary conditions. So wherever we have theta, we need to replace it with that sum. And we'll just make the choice of writing only 3 terms. And so the way we'll write it down is going to be 1 over eta, big bracket, so eta comes in as eta, then 1 plus epsilon is going to multiply maybe 3 terms out of there, So first term is epsilon naught. Second term is epsilon times theta 1 divided by 1 factorial. So epsilon and epsilon becomes epsilon squared, and theta 1 and 1 factorial is just 1, so I'm going to leave that like this. And then I can keep writing this, but let me, instead of that, what we'll say is, and then there are higher order terms. In fact, because there was an epsilon outside, so even the theta 1 term has become order 2. So if I just wanted to get the first correction, I will combine them and say these are order epsilon squared. I'll say a few things about that in a second. And then this is just this part of the term. Now we need the derivative, d theta over d eta. And that derivative is going to be derivative of, because only the coefficients have eta dependence. So this coefficient appears, then the next coefficient appears, and then everything else is higher order. Okay, so far I have this term, this term, this term. So I should close this, and then I have the rest of it, which is 1 plus epsilon theta naught plus order so the only problem with perturbation solutions is that they involve a lot of algebra. So now I have this equation. In this equation, I have theta naught, I have some theta 1 terms, I have some derivatives, and so on. But this is just this is just our differential equation. And what we will say is, so we are already anticipating that we don't need higher order coefficients. So we are anticipating that only theta naught and theta 1 will be evaluated. All terms with epsilon squared and higher powers are recorded as ordered. And I tell students, if they want, they can always do the next step and retain the order epsilon squared terms for the fun of it. And it's a very good way of spending a Saturday. So if you want to try it, you can try it. I'll see if in a homework problem I want you to go through that. But it's a nice to. So now we also need to expand the boundary conditions in the same way. And my first boundary condition has d theta over d eta, so I'm going to get gain theta naught over d eta. This has to be evaluated at 0, plus epsilon d theta 1 over d eta, which also has to be evaluated at 0, plus order is 0. And then the other condition gives theta naught at 1 plus epsilon theta 1 also evaluated at 1 plus order epsilon squared is 0. So essentially what we've done, which is new, is we've said that somehow a temperature can be expanded in this form, and then we use that series here, and we do it very carefully because we need to make sure that we are taking the right derivatives, multiplying with the right things, have the right parentheses, because if you make a mistake in the first step, then it becomes hard to solve the problem. So from 7 to 9, you actually generate a sequence of problems. And these sequence of problems include, if you want to figure out this theta, you'll need to figure out all the coefficients. So coefficients that we decided to figure out are theta naught and theta 1. And if I look at my equations, I have theta naught here, I have some theta naught here, theta naught here, here as well. And so there's going to be, the steps include pulling out all the terms that, so we'll say the order 1 or order of epsilon raised to power 0 governs theta naught, right? And so to solve that order 1 problem or order of epsilon raised to power 0 problem, we are going to make the assumption that, let's ignore all terms with positive powers of epsilon. So epsilon, epsilon square, all those terms are going to be ignored, and then I write down whatever is left. And what is left is 1 over eta, d over d eta, eta d theta naught, d eta plus 1 equals to 0, and d theta over d eta naught, and so this is theta naught, is 0, evaluated at 0. And the last one is theta naught at 1 is equal to 0. So we did all this, and then when we look at the order 1 problem, when epsilon is equal to 0, this reduces back to these equations, this equation and that equation, when there is no temperature dependence. So that's a problem we solved last week. That's a problem that you already have a solution for, right? This was a problem that gave you, I'm going to erase this part of the board. So that's a problem that gave us a parabolic dependence of temperature distribution, and if you remember it, think what you'll find is that solving this with those two boundary conditions gives you theta naught eta as 1 over 4 1 minus eta squared, and this was the solution when you had a Beer number much greater than 1. The prefactor is slightly different from the prefactor you had in the previous problem, and that is because our scaling is slightly different, but it still has that parabolic dependence, right? So I now know theta naught. We need to, next, we solve order epsilon problem. And that requires us to go back, look at this equation carefully. So this has epsilon, but then this is multiplied with this term, these terms. So you have to open the parentheses, figure out which ones have epsilon in front of them. Whichever ones have epsilon squared, we are going to drop those terms. And here you have an epsilon. And then I'll also look at my boundary conditions. Here is an epsilon, here is an epsilon. So we just pick out terms that have that are order epsilon, and that becomes 1 over eta d over d eta multiplied with theta naught d theta naught over d theta plus d theta 1 over d eta plus theta naught equals to 0, and I'll get to boundary conditions, which you can see again. This is the only term from the first boundary condition that is order epsilon, and this is the only term from the second boundary condition that is of the order epsilon. So I've generated a different differential equation, and this differential equation would have been hopeless to solve if it was not for the fact that we already know theta naught. Since we already know theta naught, we are just going to use that value here, and that allows me to simplify this, take care of this, and then we'll get a differential equation for theta 1. Okay. So that's what we'll do. So now that's where the algebra kicks in. Again, you have eta. You can do this by writing 1 minus eta squared divided by 4, and then you have the derivative, so minus 2 eta divided by 4. That's just this term. So let me put parentheses like this, and then d theta 1 over d eta comes in just as is. Close this, and then you have theta naught, which is 1 minus x squared over 4 is equal to 0. It starts to look cleaner, but of course there's still lots of terms here. But still, it has only d theta 1 over d eta, and then you take another derivative of that. So you can see you can have d squared theta 1 over d eta squared, and everything else is just a function of eta. Right? So that is the equation. Solve and show using boundary conditions, those two conditions. You can solve it and show to yourself. Again, a good idea for Saturday, Sunday, any day. You can do this over brunch while waiting for your orders. And so I have the first two coefficients, and that means I have the solution. So my solution is just going to be theta is equal to theta naught plus epsilon times or divided by 64 1 minus eta 4 plus order epsilon squared. If I wanted, I could have written the expansion to include theta 2 as well. So if I had theta 2 here, I would have had few more terms, but this board is not long enough, so we're not doing it. And then those few terms would give me, after this step, I would say, okay, I have theta naught and I have theta 1. Now I'll write down the equation for epsilon squared, order epsilon squared terms. You make use of these two that you've already calculated and redo this, and then get another term. But you can already see this. This is 1 over 4, and this is epsilon over 64. So compared to 1 over 4, 1 over 64 is already much smaller. And because of this epsilon, this term is going to be very, very small. And if you try to put numbers based on size of a regular wire and whatever you know about the HV value and K value for typical wires, you might find that this correction is more or less, this is a good mathematical exercise, but doesn't really do much because the first order correction is very, very small. And then if you go to a system where your delta T is large or your heat source term is large, then your regular perturbation analysis is not applicable. You just have to solve the whole problem numerically or otherwise. But whenever you can solve this, it's satisfying for one. And the other place where this is used a lot is, say, in linear stability analysis. So we'll talk about linear stability analysis later, and maybe some of you have been used to it. I will always remember regular perturbation for one more reason. When I was a postdoc at MIT, we visited UK, so I'm going to erase this while I tell you the story. So the main thing you have to remember is the success depends on whether we can solve the order 1 problem. If we can solve that problem, then we can continue this part. And sometimes even that is not possible, and you just have to do things numerically. All right, so that's the end of what we do for now in terms of perturbation analysis. We'll start with transport and electrolytes, and I will introduce singular perturbation analysis using an example from transport and electrolytes that's not given in the book. We'll do that example maybe next week, and once we do that example, this will complete our discussion of chapter 4. All right, the story. So when I was a postdoc, I was in this jet lag state. We had to present to our sponsors, and after that presentation, we went to it was near Windsor Palace, very nice setting, and we were sitting outside drinking pins, and then the industry guy who was sponsoring the research asked a question, and he said, "No, I don't understand this derivation." And so my postdoc advisor was like, "Oh, Vivek can derive it for you." So I'll always remember sitting there, watching these swans go by on River Thames and doing a long perturbation analysis. Yeah, so you never know when you'll be called to do this. So this is a useful skill. All right, so we'll, I think in your book there are 3 or 4 examples, and there are some, I think, 4.32, 4.33, some homework problems, and also in VSL there are a few. In chapter 10 there is again the heated wire problem, and I don't remember if it has the same boundary condition. Then there's a viscous heating problem, and I don't remember what 10C3 is, but and if the need be, we can always come back and look at some other examples of regular perturbation. So make sure I'll assign the problems tonight, and hopefully, and then you can start doing this kind of problems for the fun of it. All right. So now we are going to look at transport in electrolytes, and I think I took overall 26 graduate courses, but nobody taught me this. So I'm trying to make up for it by teaching this to my students. So transport in electrolytes is something that is going to be very important for anyone who ends up working in electrochemistry. Could be for doing electrolysis, could be for separations, could be because you are trying to design batteries, and these separations could be in water treatment. You often encounter electrolytes. Water is an electrolyte, and it always has salts, which then influence behavior of lots of things. So that's one context. Or if you go work with membranes, and even in biology, there are membranes that require you to understand interplay of charge and transport. Like one of the simplest and my favorite example is if you think about a cell membrane. A cell membrane has water inside and it has water outside. So there's water inside, water outside, and it's separated by a membrane that's formed by lipids. And those lipids have head groups that love water, they're hydrophilic, and they have tails, which are these long 12 to 18 carbon long chains that hate water or are hydrophobic. And so when you put too many of these lipids in solution, they figure out that one way to avoid hydrophobic areas having contact with water is to self-organize and form these things, which if you have nothing inside and nothing outside are called vesicles or liposomes. But if you have all the living matter inside, then it becomes a cell. So that's how, so you've learned now how life came into being, and that's the end of story. But these phospholipids end up being charged. So typically they are charged, and they have, in water, what happens is there is some kind of a counter ion, which could be a sodium ion, for example, or hydrogen ion, and that counter ions will be just diffuse around it, and they will form what we call a double layer. So we'll talk about double layer. But eventually you really need to understand that the fact that not only these membranes are charged, most of the proteins might carry some amount of charge. Many of the biomolecules will carry some amount of charge. And so when you have to transfer those charged species from outside to inside, apart from thinking about everything that we've learned so far in context of diffusion, the critical idea is that whenever there are charges present, they'll create a potential or they'll create an electric field. Whenever there's an electric field, that is going to influence motion of charges. And because of this relationship that charges creates fields and fields affect charges, in charge systems you always have to keep solving for the field or the potential, and you have to figure out how things are moving in presence of that potential. So that's example of how this gets used in context of cells, and again, blood is also mainly water and has lots of things, biomolecules, proteins that are floating around in it, and many of those are charged. But even if I go to more mundane things, something like foams that I like to spend a lot of my time thinking about, or emulsions, or and you must have seen at least a dozen kinds of foams from this morning onwards. If you drank something, if you brush your teeth, if you wash your hands. So in many of those cases, instead of lipids, you have soap molecules. And those soap molecules do the same thing. They also have a hydrophobic tail and hydrophilic head group. And one of the most common surfactants is, for example, sodium dodecyl sulfate. And when we say sodium dodecyl sulfate, sodium turns out to be the positive ion, and dodecyl sulfate, because of the sulfate group, is negatively charged. And you put this into solution, it immediately, just like when you put salt, regular salt into solution, it gives you sodium ions and chloride ions. And when you put this in solution, they are able to maximize their entropy by spreading out. Right? So that's what they want to do. They want to maximize their number of states by being wherever they can be. And yet, if I have a surface, any kind of surface, it could be this surface, or it could be the container. On the container, you can have charges for various reasons. You might have similar kind of functional groups that cause it to be charged. So once I have a charged surface and these ions start to come close to it, there's going to be a competition between two things. If I just consider the counter ions, oppositely charged ions, then those oppositely charged ions are electrostatically being attracted to this. And so that is going to give you some kind of, so they would want everything to be squashed against this wall, right? So electrostatic attraction between counter ions will try to bring everything close to this. But osmotic pressure or entropy wants everything to be diffused away. Or everything we learned about diffusion was how you want to make concentration gradients disappear. So that balance between electrostatics trying to squash everything and entropy trying to expand everything gives you a particular distribution of ions around it. And that distribution of ions is the so-called electrostatic double layer. We'll sit down and derive how ions are distributed in space. And that is very important because it then tells me if I bring in two surfaces like this close to each other, if I try to bring two surfaces close to each other and they have this cloud of counter ions in between them, the closer I try to bring them, the more restricted is the space available to counter ions. And that they don't like because then their entropy has to go down. So this causes some kind of a repulsion that's always present in all colloidal systems that have any charged surfaces. And that repulsion then will be balanced at some distance, and that distance you can determine and so on. So for the stability of foams, emulsions, proteins in solutions, all kinds of inks, all kinds of paints, the basis is how when you bring surfaces close to each other, the so-called intermolecular and surface forces come into play, and this is one big part of it. So if you go and work in at least half of the groups in soft matter, or maybe all of the groups in soft matter, will end up using some of these ideas at some point or the other. And if you go to industry and you want to design a better paint or ink or any of the cosmetics, a lot of time is spent in thinking about these. So even if I design something that works very nicely in the lab, and then I go and use, instead of DI water or tap water from my lab, I go and use seawater, the salt concentration changes, and that will change all these interactions. Something that was nice dispersion will actually become particles are separated from the rest of the thing, right? So those kind of ideas are why we really want to understand this in great detail. And we also want to understand this in context where you're trying to maybe pump out, so in separations, you might be using membranes so that you can filter out all sorts of gunk. And one set of separation happens just because of size. You can just have a membrane which acts like a barrier, so your drinking water does not have all the things that float around in Chicago River, for example. And then you have to have smaller and smaller membranes that take care of, you don't want arsenic in your water or lead. I guess everyone has heard of that story. So there have to be membranes that do that. And there you might have very small pores through which you're transferring, and those pores can have charges on them, and you're transferring ions through those pores. So the effective size of those pores is quite different because of interplay of how counter ions interact with those surfaces. And I think you will probably have a separate course on water treatment or things related to water, and most of the things that if you work in membranes, you probably need to learn on your own unless there is a course on mass transfer. But this few weeks, we'll get a flavor of kind of things you want to look at. All right, so that's sort of the very quick reason why we want to discuss charge transport, and as you become more and more aware of what you want to do as researchers, you will find that some topics covered in transport or thermodynamics or mathematics course are more relevant for you. But I can assure you that irrespective of whether you go to industry or academia, you're always going to talk to people who are not in your field. So all this helps a great deal on a daily basis. All right, so the first thing, and this is all mainly based on Dean chapter 15, but wherever Dean is inadequate, I've added things from Newman. That's the best book for electrochemical processes, and for a few other books, and I'll try to mention those whenever I can. So the first thing is we want to figure out what happens when there is electric field, how that affects transport, and it turns out that whenever you have charged species, there's going to be an electric force on an ion, and we're going to do this on a molar basis, so per mole. So electric force on an ion per mole is Zi, F, and E. All right, so each one of these, E is electric field, and that is a negative gradient of chemical potential, or not chemical potential, electrostatic potential. So in all the other cases, we had a gradient and some quantity that was driving transport. In this case, it's going to be gradient of chemical potential that's going to drive transport. And so among other quantities here, this Zi is the valence. So you can have things like sodium that have +1, chloride that has -1. So that is positive or negative integer. Tells you what charges you have and what their sign is. And F is Faraday's constant, which allows you to go from charge to moles and moles to charge, because F is defined as Faraday's constant, and this has a value of 9.652 into 10⁴ coulombs per mole. And whenever I write ZIF, this represents charge per mole. And maybe some of you remember Coulomb's law. So if I was looking at force that acts between two charges, Q1 and Q2, then you have this inverse square law, which is again one of the forces that people already knew about almost 200 years ago. And this we can also write as Q times electric field. Again, I wrote magnitude there, so let's just put this way. And this Q is either valence times the charge of an electron, or if you want to write everything in terms of moles, then you just write Zi here. So that's something you might have learned in high school, but main thing you need to know is that whenever there's electric field or gradient in electric potential, there is going to be an electric force on ion per mole. And you already mentioned that there are all sorts of processes where you need to think about this. And the other idea I said, which is important to understand and will be emphasized to all the problems we do in this context, is ion fluxes are influenced by electric field, which in turn depends on ion concentration. And because of this kind of coupling, whenever you have coupled equations, they become nonlinear very quickly, and there are not that many cases that you can address analytically, and that also makes the problems difficult, which means less people work on those. And if less people work on those and you know those things extremely well, then you become famous very quickly. So this is what you do to become famous quickly. So I'm going to give you again a visual representation of what happens when you have surface in contact with salt acquires charge. Alright, I should write bigger. And then you're going to have if I have to draw this well, then I have to understand that there are counter ions that attract to the surface, and there are co-ions, similarly charged ions, that are repelled by the surface, but what that does is you get, if I look at the spatial dependence, your potential decays away from the surface, and if I look at the charge density of counter ions, for example, that also decays away from the surface, and whenever something decays like this, let's say this is x direction, we are always interested in figuring out what is the typical length scale to which this influence is extended. So that typical length scale is called Debye length, and that Debye length is a very important parameter. I think if you spend any time in Tyrrell group meetings, or maybe also in Juan's group meetings, you'll hear that repeated almost on a weekly basis. Yeah.
I don't think I fully understand what's going to cause charge to go up on
Yeah.
surface,
So
just a general surface in contact with my ions.
oh, so what will build up charge in contact with the liquid? Yeah. So that's a good question. So I could have so there are 2 or 3 mechanisms. One of them is they could be just absorption of some of the species from the liquid itself. So there can be chemical or physical absorption. So that is kind of a thing that would happen, for example, in biological fluids. You have proteins, and proteins might like the surface for no other reason than the fact that if you use, say, plastic is going to interact very nicely with the hydrophobic regions on the protein. And then they can come in contact, but other parts of the proteins are charged, so then that protein will build up the charge. There are other cases where this charge will arise from specific functional groups on the surface, which then in presence of the fluid like water or a salt solution are going to ionize. And that ionization is very important when you're thinking about many of the membranes, many of the polymeric membranes that are used are polyelectrolytes. And if has there been any talk on polyelectrolytes yet? No? You guys should have more seminars. I should give this feedback to Matt and Juan. So you should at least look at what they do. Then you'll see that polyelectrolytes, why they're spending so much time on thinking about not just polyelectrolytes, but again, in the biological context, it's going to be all this, because these kind of species, when they self-assemble, that is forming a surface too, right? So that surface is charged because the ingredients are charged. And then, of course, there are related questions. If you get a charged surface, how do you find what is the amount of charge you have on it? And we'll talk about things like zeta potentials. And those are all very important concepts. And here, the idea that is critical is entropy wants to spread out things, because if you're taking, I guess this from Juan, and if you are taking it from Juan, taking thermodynamics with Juan, he probably is teaching you Stuckneck. So in statistical mechanics, you just count the number of states, and you'll have maximum number of states if you can roam around, if access to all the solution. But electrostatics is trying to restrict you. And they are trying to restrict or confine ions, and between the battle of these two, make sure that there is some length scale, lambda d or Levi length, to which you get sort of a cloud of ions, and there's a distribution which we'll calculate. Now if I go far away from that kind of charged surface, the system is electroneutral. And even if I count all the ions that are near the surface and on the surface, everything aggregated together is going to be electroneutral, but locally you can have charge distributions. And we want to understand those local charge distributions because they influence stability in case of colloids, they influence transport through membranes, they influence the functioning of electrolyte. So they allow you to do electrochemical reactions, or they allow you to produce electricity from those electrochemical reactions, depending upon what your application is, right? And I think if you pay attention, you'll know that there are lots of even utensils that are electroplated. So all those processes are, some of them are very conventional things, but when you start doing research in sort of, say, area of batteries, that's one of the things that everyone is trying to invest in, and maybe some of you will set up the new big companies that will use these to solve the world energy problem, and then give more funding to UChicago to have another building and more engineers. That's how this goes. All right, try to write on this side again. So we'll be deriving all that. So I just want you to have a sense of where this is headed. So we wrote down the electric force on an ion per mole, and that electric force is something that is now going to influence the transport. And to figure out how it influences the transport, we have to go back and start thinking about everything that, so we already know there's convective transport, we already know there's diffusive transport, so we will probably be adding another term to it, and that term is called migration, and we need to figure out how to write that migration. So, in general, this is something that comes from non-equilibrium thermodynamics, so we'll just accept it for now. For particles or ions, force is equal to 1 over mobility times velocity. Or equivalently to some kind of friction coefficient. So whenever you move through a fluid, you can feel some resistance. So that's, resistance is of course there because of viscosity, or how momentum is being transferred to or is lost to fluid around you. So that's the force. And for that force, one example is the Stokes drag, which we mentioned earlier, is always relevant when we have low Reynolds number flows. So Stokes drag is what bacteria feels when it swims around. Stokes drag is what many of your red blood cells might feel when they are in blood. And this is the friction coefficient for a sphere, and we will derive this in class. So we'll redo what Stokes did like 150 years ago or 140 years ago. So friction coefficient times velocity gives rise to a force. And I can write this as, actually let's just retain only the symbol that you need for Dean, otherwise I'll confuse. So in case of Dean, you would write this as U times FD, where U is mobility. In some textbooks they use M, in other textbooks they use other symbols, but so if I have an extra velocity that gets contributed by an extra force, then this is going to be on top of whatever velocity you have because of flow, whatever velocity you have because of diffusive flux. And that's the primary idea. So we already know the force on an ion per mole, and because we already know the force, the mean velocity, so this is mean velocity. Each ion might have slightly higher, slightly lower distribution, and also it will have Brownian motion, but the mean velocity resulting from electric force is going to be, I just need to multiply with mobility. And if I have many ionic species, so mobility for species I multiplied with charge for species I, so ZIF, multiplied with electric field. And to retain the idea that our flows or transport is being driven by gradients, I can write this also in terms of chemical potential, and then there's a negative sign. So that is my field. And what is the flux? Flux is just Ci times velocity. So I have an extra flux that is going to be this term multiplied with Ci. So what we need is corresponding flux, and that is just whatever we just wrote on, Zi, Ui, F, E, that was the velocity multiplied with concentration. So this is an extra term, and this term is called migration. That's something that, at least in Dean, they use migration. And if you go and read some old book, I somehow started reading this 1970 book, and they kept calling it conduction, and that was very confusing, because you associate different terms with different formulas, and yet you have to learn this, that this extra term is going to be superimposed on diffusion and convection. So if there is no flow and no charge, then you have only diffusion to worry about. If there is flow, then you'll have more material reach a particular surface per unit area per unit time because of convection. And then if there is charge, then there could be a third contribution. Therefore, total flux for an ion I in dilute solution. Most of the things we are doing are appropriate for dilute solution, because in dilute solution you can change chemical potential gradients very easily into concentration gradients. And this is the important formula, so let me write it in some other color. So your Ni has convection, diffusion, and migration. And again, you can choose between potential gradient and this. So this is, in Dean, this is equation 15.21, right? And Di is your pseudo-binary diffusivity, which when we say pseudo-binary, it means you might have two different species maybe floating in water, and so in that case, the concentration is so low that you can use most of the binary diffusion conditions. And then I could replace this by Zi, Ui, F, Ci. So I have minus and minus here. So this is a transport coefficient. And so is this one. So if we can actually measure both those quantities. So you can measure those quantities, and these equations are useful as such. But there's an additional simplification that can be done for dilute solutions. So as transport coefficients can be used as such or be measured. This description is complete in itself, but you can do additional simplification. As soon as you recognize that in this case your diffusion itself can be written as RT times UI. So this is an equation that is called Nernst-Einstein equation. And of course, some of you might recall we had written a similar equation called Stokes-Einstein equation. And in Stokes-Einstein equation, we had KT over the friction coefficient. And 1 over friction coefficient is mobility, so there's an analogy between those two. But this idea comes from the fact that the driving force for this transport is gradient in electrochemical potential. We'll write this sentence formally next time, and we'll also write the chemical potential and electrochemical potential next time. But once I have this Nernst-Einstein equation, I can use this Nernst-Einstein relationship to get rid of either UI or DI. And in this course, we've been focusing a lot on diffusion, so we'll retain DI. And if we retain DI, then we get the final equation where we'll end for today, and that is the Nernst-Planck equation. So Planck was working on these things before he, I think before he got the Planck constant and everything, quantum mechanics started. I hope it's the same Planck. I should check that. I just realized that I was saying that without having gone through. Sometimes it could be Planck's father or uncle. In Bernoulli's, you have to be very careful. So if I do that, use the Nernst-Planck equation, then we get the Nernst-Planck equation, and again there is the convection term, diffusion term, migration term, and what we also get here is RT over F. Now if you think about all the units or dimensions, this is CIB. This we already remember should be same units as CIB, so that's all fine. And here we have other things. You have gradient in potential, and you have RT, and you have F. So one way everything becomes consistent with this is if your potential divided by RT into F was dimensionless. So it turns out this term RT over F appears a lot in these kind of calculations, and it's called thermal voltage. It has same units as phi, which means it's in volts, and at 25 degree Celsius, this RT over F is equal to 25.7 millivolt. And if you remember this quantity, then you'll know that in most of these cases we'll be dealing with some millivolts. And for completeness, you can also remember that if I multiply both numerator and denominator with Avogadro's number, then I end up with RT over F. So if you go to a different textbook, they might be using notation where they have Boltzmann constant, charge of an electron, instead of Faraday's constant and the gas constant. So we'll start from here next lecture, and we'll go through some very important ideas about transport and electrolytes, and hopefully that will be a sampler for you to get you prepared for membranes or colloidal dispersions or polyelectrolytes, etc.